Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech, and this is my quarantine here. And I would like to welcome you to the 6th lecture in the summer 2020 offering of GPU programming for video games. So the main method of lighting we'll look at in this class is local illumination. So we have a light that shines directly on an object, and we're not looking at light that's bouncing off of other sources. And in particular, and kind of oddly, at first glance, we're not going to worry about the fact that there may be something in between the light and what's being lit. Now, there are techniques for including shadows, but these require a lot of work. We'll look at some of them in this class, but it's pretty complicated to incorporate it. Global illumination would include light bouncing off of other objects, so you might have something over here that the light will come in and bounce off of. This makes for much more realistic scenes, but is definitely computationally intensive. Now, a full-fledged version of this would use something like ray tracing, and although in the past, about 10 or so years ago, there were people using the GPU capabilities of these graphics cards, the scientific supercomputing part, in order to do ray tracing, those were generally not real-time computations. The latest cards from NVIDIA and ATI do have some sort of real-time ray tracing capability built into them, but it's still somewhat limited, and there's not a lot of games that use that capability, and even the games that use it only use that real-time ray tracing for certain effects. In this class, we will look at global illumination, but we'll basically look at clever ways of faking global illumination effects. In 2012, there was a conference where a researcher at Disney published some of their work that they're using on what's called physically based rendering in movies. And it seems like every graphics programmer in the game industry either saw or read that presentation, took a look at that work, and decided to try to start putting it in video games. So this was an extremely influential piece of work. Notice that using physically based rendering doesn't necessarily mean something's photorealistic. So here we have a couple of characters that are definitely not things that you would see in real life. The main idea here is that even though the characters themselves may be highly stylized, the various materials that make up the surfaces of the characters do respond to light the way sort of real materials respond to light. And the main thing this gives you is the ability to drastically change the way a scene is lit without having to go back and change the way that you are defining the material properties on your objects. And also, very importantly, physically based rendering doesn't automatically imply that the scenes in your game are going to look good. Certainly, you can buy a bunch of cameras, you can buy a bunch of lights, and you can try to shoot your own movie. But unless you have some experience in knowing how to set up those lights and set up those cameras, your production is still not going to look terribly professional. So here's a fantastic example of using physically based light and the Fox engine that was used in Metal Gear Solid 5. And I'm going to pause here for a second and give you a chance to look over this and try to figure out which scenes are an actual photograph of a conference room at Kojima Productions and which one is rendered by their engine. So there's a couple of main tells here. One is the reflection off of the posters. These are behind some sort of coating that's giving it a glossy reflection. And you can also see some subtleties in the way the light is working here. If we look over on this side, you can look at the reflections coming from these light sources that kind of blur out over here in the scene on the right. I may be reading too much into it, but I think there's also some more subtle details on the backs of the chairs here that are on the right. And you can also see the same thing about the glossy covering on the posters. So same question, take a look at these scenes and figure out which ones are real and which ones are created by the engine. Okay, that was a trick question. They are all created by the engine. They did not actually bring a horse into their conference room. This one is obviously not real. You generally don't have things floating in space like this, but this is fairly impressive. I should give credit to a former Georgia Tech student, John Hable. He was working at Naughty Dog doing video game graphics for a while. I think his most recent gig is at Epic Games. He has 2 truly fantastic blogs, and you'll find consistently that the latest, greatest information for graphics and games is not something you'll find in scientific research papers and things you'll find in textbooks. It's usually in the blog posts by people who are trying to make these things work. So John has a Bachelor of Science and a Master of Science in Computer Science from Georgia Tech, and his blog has had a big impact on the way I think about physically based writing. His older blog, Filmic Games, isn't up anymore. You need to go to the Wayback Machine to find those articles, but they are still fantastic and still very applicable. So when people talk about physically based rendering, it's not one specific thing. It's sort of a combination of a lot of different factors. The question of linear space lighting, this largely has to do with the way that textures are authored and stored, and I'll deal with that in a future lecture. 2 very important properties that we'll detail later in this lecture are energy conservation and reciprocity, and these are particularly important if you are going to try to perform some sort of global illumination calculation. Physically based rendering also makes a big deal about whether things are metallic or dielectric. As an electrical engineering professor, when I see the term dielectric, I automatically think about capacitors. But for our purposes, for this class, dielectric basically means not metallic. So anything that's not a metal is a dielectric. Previous techniques in computer graphics that were less physically based and more based on heuristics didn't have such a distinction. Another interesting thing about creating a physically plausible model is that everything has specular reflections. Again, we'll define those later in the class, and we'll talk about it a little bit later in this lecture. Even things like cardboard that you don't think about are shiny still do have specular reflections. And everything is going to have what's called a Fresnel effect. You can think about if you're driving along and the road is made of blacktop, you don't think about that as being very reflective. But if it's been raining and you're at a certain grazing angle with respect to the sun, so the sun's at the horizon, that can essentially blind you. That road turns into a mirror. Now, in order to fully benefit from physically based rendering, it is good if we can actually have a level of resolution and a dynamic range in our video buffer to be able to handle the high dynamic range of realistic light sources. Graphics techniques used in earlier games typically dealt with the limited dynamic range available in our memory buffers where we store the results of graphics calculations. You pretty much handle it by having very restricted ranges of possible light intensities. But realistic scenes that are physically plausible can have a wide range of different light intensities. Your eyeballs handle this by sensing light intensity on a logarithmic scale. It's the same way you perceive musical pitch. It's the same way you perceive auditory volume. It's why you can perceive both a jet engine and a pin dropping on the floor. And then there's a set of techniques to take that high dynamic range image and map it to the limited range of your display. Again, we'll talk about those issues in a future lecture. Modern game engines can handle a variety of complicated light sources, even in real time nowadays, but we'll stick with the simplest ones for most of this class. So we'll imagine that a directional light source consists of a bunch of rays that are coming basically parallel from something that's really far away and very bright, something like the sun. Something more local might be a point light, energy radiating in all directions, but that energy is going to fall off with distance. So as you get further out, it's going to be less intense. The same effect technically is happening with the sun, but the sun is so far away that these rays that are radiating out like this basically seem like parallel rays as far as something the size of the Earth is concerned. As we get further out, the light intensity of this wave keeps being distributed over a bigger area and hence keeps dropping. But the Earth, or whatever our scene is such a small limited range of ranges, such a small limited range of ranges that relative difference doesn't make much difference in terms of calculating the attenuation. So you assume that these things over the course of your scene basically have the same intensity. So a spotlight you can think of as a refined version of this point light that emphasizes particular directions. So if we think about our objects sitting here in space, we'll have a happy surface, and we'll think about the normal coming out of that surface. This is going to be essential for the lighting calculations we do. We are also going to be concerned with the direction vector pointing towards the light source. Some calculations we look at later in the class, not today, are going to deal with a vector that's reflected at an equal angle around the normal. There's going to be a vector pointing from that point on the surface or trying to light towards wherever the camera is. And computations we look at later are going to involve this thing called the half vector, which bisects the light vector and the eye vector, or the viewing vector. We can compute that bisecting vector by just basically averaging the vectors, but then normalizing them again. And I should mention, all of this computation assumes that these have been normalized to have unit length. So these have a length of 1. This has a length of 1. Everything here has a length of 1. This normal here has a length of 1. The light, the vector, everything's been normalized to have a length of 1. And I'm emphasizing that because an extremely common error in doing graphics programming is to forget to do that normalization. And there are several places where that can turn into a problem. One thing I want to emphasize is that these normal vectors are not the normal vectors we talked about in the backface culling lecture. Those are things we're kind of computing on the fly for a particular triangle, imagining that triangle is flat. These normal vectors are derived from normals computed by the software used by your 3D artist, something like 3D Studio Max or Maya or Blender, that for each vertex will spit out a normal that's used in these lighting calculations. And those normals created by the software try to encapsulate some information about the underlying surface that the 3D model is trying to make a coarse tessellation of in order to spit out triangles. So lighting has diffuse and specular components. I'll briefly talk about specular later, but specular is so complex that I would like to do that in its own lecture. So right now we'll just talk about diffuse lighting. So diffuse surfaces are surfaces that are rough relative to the wavelength of light that's illuminating it. And that's from the point of view of the light. It may not look rough to your eyes. A fun thing to do is to take a laser pointer and aim it at your table and hold it at something of an oblique angle, and you'll see this weird spotted pattern. That's because the coherent light coming out of the laser in your laser pointer can expose these rough details in a way that general incoherent light, which is coming out of your light bulb, coming out of a candle, coming out of a sun, is going to give you. So because the surface is so rough, basically, when the light rays come in, the energy that's coming in is evenly dispersed because of the randomness. So it doesn't really matter with diffuse sources where the camera is, as long as the surface is within the visibility range of the camera itself. So how does that work? Here we're going to get into some physics. So we're going to say that if the light and the normal on the surface are lined up, we've separated them slightly here just to try to not get the light vector and the normal vector confused, but you should really think about these as being on top of each other. If they are lined up like this, and again, I should mention these are both assumed to have unit length. It's not clear from the way I did the graphics here. Anyway, those should both have unit length. So now if the light's coming in at an angle relative to the normal, again, it doesn't matter where the camera is, we're going to have less light reflected towards us. And if we're coming in at a 90-degree angle, there's essentially no reflection. So the kinds of reflections that we get, depending on the light, that follows the cosine law of the cosine of this angle. And the nice thing about this cosine drop-off is that you don't actually need to compute a trigonometric function of cosine for an angle. You can get that cosine using some trigonometry. It's just the dot product between the normal vector and the light vector. So here you're taking each of the coordinates, x, y, z, and you're multiplying the x of the normal vector with the x of the light vector, the y of the normal vector with the y of the light vector, the z of the normal vector with the z of the light vector, and adding those up. So we'll also take this max here, because if we don't, the cosine here will happily go negative because of the computation, but that means we're illuminating this object on the other side, and obviously nothing is going to reflect there. So what else is going on here? C light is the RGB color of the light, so this is a triple, and MDiff is an RGB color of this diffuse reflection. And the strange little multiply symbol here with a circle around it, this is a color-wise product. So this is red times red, green times green, blue times blue of that triple of color values that gives you another color value. So for the double E's in the class, this doesn't represent convolution. This does not represent some sort of weird Kronecker or matrix product, if you've seen those. It's just red times red, green times green, blue times blue. So specular reflection is more complicated. Specular reflection is something that depends on the viewing angle of the camera. And if we add that effect to the diffuse, and here I've also added a little bit of ambient light. So this is a bit of a legacy from earlier versions of this class that used more primitive, ad hoc, heuristic lighting models. Ambient's basically just a bit of light you add to everything that in an older game engine would try to represent sort of a general sense of bounce light all around the scene. Nowadays, we have much more advanced techniques to handle this that we'll look at later in the class. Specular lighting in earlier versions of this class used something called the Blin-Fong model. The Blin-Fong model is not physically plausible in ways that we'll see later. Now, we can use some physically based specular models that are inspired by this. We'll talk about that in a future lecture. The formula that I showed you earlier looked very much like this if we did not have this part here, right? If we just put this diffuse color here, then that equals what we had before. So what I'm showing you is a slightly more sophisticated and more general view. So here we have that Lambertian term, that computed diffuse light, but now we're including something called the bidirectional reflectance function. This is a function of that angle with which the light is coming in. Although I should say when I say coming in, the convention is that the light vector is actually pointing towards the light source. And same thing with the viewing vector. It's pointing towards the eyeball. So there's the eyeball. Okay, now for the case of diffuse lighting, there's a very simple bidirectional reflectance distribution function, and it's just a constant. It's basically this material color. This allows us to later include specular reflections by having a more complicated BRDF where we can just add some sort of specular term to it and easily incorporate the diffuse reflections that we've already looked at. Now, you maybe wonder what's going on with the pies. So this gets into some of the more gory details of the technical mathematical underpinnings of computer graphics. The BRDF here has a pi in the denominator that acts as a normalizer in the way this thing is defined. I've toyed around with the idea of putting more mathematical details in this class, but I ultimately decided that for the purposes of this class, I would like to focus a little more on the programming aspect. And there's all kinds of books and papers and blog posts you can read if you want to get more into details about things like, why is there a pi there? Fortunately, again, if you go to the underlying physics of math, for most of the lights we're looking at, or at least the lights we've looked at so far, there's a pi factor that just shows up in the physics of this formula. And beautifully, if you combine these, those pi's wind up canceling out. So when you look at shader code, you have to pay attention sometimes, because sometimes you'll see a pi appear in a formula, sometimes you won't. Sometimes you'll see a BRDF like this where there's a pi in the denominator, sometimes there isn't. If it's something more complicated that's not diffuse, maybe it shouldn't have the pi. It can get complicated because people will often say, well, I've got this pi in two places, and if they wind up canceling, why bother putting them in? Why not save the computation? So BRDFs, to be proper BRDFs, i.e. to be physically plausible, and that's what we're looking for. We're not trying to perfectly match all the laws of physics that describe your scene. We're trying to find models that may be approximate in certain ways, but at least sort of adhere to some basic physical properties. And here, the reciprocity means that we should be able to change the location of the light source and the eyeball, and you get the same thing out. That's called Helmholtz reciprocity. Obviously, for this diffuse lighting BRDF we've looked at, well, it's just a constant, so it satisfies that. But very importantly, that Blin-Fong model that I mentioned earlier, this does not have this reciprocity property. So another important thing BRDFs need to have in order to be physically plausible is they can't reflect more light than what's coming in. Again, here we're talking about reflections. You can also have emissive surfaces, things like a neon light, or if you think about on your electric stove, if you pass a current through your heating element, it doesn't just get hot, it also glows, it creates its own light. Technically, for our diffuse model, it turns out that you can't just pick any MDiff you want. It has to be less than 1 over pi. So pi times mdiff needs to be less than 1. Again, that goes back to some of the underlying physics and math, which I don't really want to get into here. But, it's just a constant sitting there. So usually, as this source, Steve McCauley noted, quite often people don't worry about this pi. You just say, okay, we're going to go with a certain convention and just say that, artist, when you're authoring material properties for your red, your green, and the blue, make sure each of those numbers is less than 1. And then that sort of gives a natural thing. If you hit something with a light intensity of 1 and the light hits the normal directly, you hit it head on with a 0-degree angle, well, you get 1 back. So that makes people happy. But one thing to remember is if you are going to be writing some sort of complicated global illumination solution that is setting up some big matrix equation of some kind of whatever that is handling all of these bounced lighting effects, then you might want to go back and worry about this, because otherwise you might get an iterative solution that goes unstable because you have these surfaces that are technically spitting out more energy than came in. Okay, so returning to our light sources again, the directional light, it's infinitely far away. We're going to assume that we don't need to worry about attenuation with distance from the light over the range of our scene. But for point lights and for spotlights, you may want to encapsulate the fact that the energy field coming out of this, if you look at the amount of energy per unit area radiating out, conservation of energy means you have less and less energy per individual bit of area that's radiating out here. So you may want to take that into account, that the light is going to drop off with range. People will sometimes use a physically based model. Sometimes they'll use a model like something like this, where there's a couple of constants that you can set to get different artistic effects. This d squared, that's physically a reasonable thing. This d is not, this linear term in d, but you might select this to have some sort of artistic effect. So there's different ways to formulate a spotlight. No particular technique is necessarily better than others. I'm going to show you one that I've seen in the CG tutorial that was published by NVIDIA some time back. You can actually read that online now for free. Anyway, here's the idea. So we'll have a vector pointing towards the point that we're illuminating, wherever that is on the surface, and we'll have another vector that represents the direction the spotlight is pointed in. Again, these are both assumed to be normalized to have unit length. And what we'll do is we'll determine a fall off based on the angle here called alpha between them. Again, we don't need to use the cosine. We can just use a dot product. One thing I want to mention as a bit of caution is that the lighting vectors we've looked at previously have pointed from the object to the light. Here, to match up with the direction vector coming out of the light, we'll have this lighting vector pointing from the light to the surface. Anyway, this dot product here computes that angle. We'll do the max thing again, because obviously if we're at 90 degrees, it's not going to be illuminated anyway. And what we have here, this f, this is a fall-up factor. And remember, this quantity here that we're taking to the power of f is going to be between 0 and 1. And so if we take the power, what that's going to do is it will take that cosine shape and it will start to compress it in different ways. So it might instead look something like this, or it might then look something like this. And so as we increase f, we're basically tightening up this spotlight effect. The Blin-Fong model I mentioned before used a similar computation to compute specular lighting and has similar control over the width of here a specular highlight, but this specular highlight I'm talking about is not the same as the spotlight effect. All right, so if you are not taking GPU programming for video games with me in the summer 2020 semester, you can check out now. But if you are taking GPU programming for video games with me in the summer 2020 semester, I would like you to do the following. If you go to Piazza, you will see a post labeled something like Lecture 6 Task or something along those lines. Anyway, what I would like you to do is the following. I would like you to once again take the first letter of your last name, and I would like you to once again turn that into a numeric value in the usual way. Let A be 1, let Z be 26. We do something in between. And then I want you to do something to that number, but don't include the thing that you're doing that I'm saying here in the post. Because the whole point of this is I want to make sure that you've actually watched the video and that you haven't just copied what you see one of your colleagues doing when responding to the post. This is just between you and me. You, person watching the video, who's a student in my class, and me. take this number and add 3 to it. Why 3? Because 3 is a nice number, and it's the number of dimensions in XYZ, and it's the number of colors in RGB. All right, so I want you to do that. That's the first thing. Now, the second thing is just tell me a little bit about your interest relative to this class. So basically, things along the lines of, why did you take this class? Why did you sign up for this class? And this reason need not to be super fancy. It could be as simple as, I needed one more class at the senior level, and this is the only one I could get into this summer, or something like that. We are offering a lot of classes, so I assume there were things that drew you to this particular class. In terms of interest, things like, are you interested in maybe writing a video game? Would you be interested in teaming with classmates, not for the purpose of this class, but outside of this class, or perhaps joining with other people outside of this class to write a computer game? Do you have any interest of later joining the game industry? Or maybe not the game industry. Maybe the game industry makes you want to run screaming, and maybe you want to get into computer architecture, and maybe you would want to design GPUs, even if you're not writing for games. Maybe you do want to do graphics programming, but you want to make simulations for training of some kind instead of games. Anyway, I'm not looking for a giant essay here, just a couple of sentences. Why did you sign up for the class? What drew you to this class? And a couple of sentences of sort of what your interests are relative to the subject material of this class.